Hi there. Like I said, I better record this. I'd like to record this test just in case it works. It would be amusing. Quite a long time ago, I mentioned something about hash tables and associative arrays or maps. This was probably during one of my rants on the standard template libraries map class, which is unreadable code as compared with the MFC one, which is based on a simple hashing algorithm. I think I said. Well, so I searched for CMap, which I know is the name of it, and came up and found their class. It is small, not that much code, and I generated these three files from that. Check this in. Trying to maintain a history. Alright, so now there's this stuff in the header file, and I copied most of it. I did some renaming, and these here are all written like this. And now this is supposed to be in a header file. Well, for one thing, I took away these ones. I only use two things: key and value, and I just take it as given that this here is going to be a constant reference to one of these, and this constant reference to one of these, and I just added these last two. So here's my version of their map. It's not exactly the same, but very similar. Now it involves using something they call a C-plex, which is a tiny little class, and I'm not sure I understand it. I have to look closely. Where is that C-plex? Well, it'll be in here somewhere. Now these create blocks of memory, and it's general. It's not to do with the map specifically. And well, reducing it, I end up with this. There's a single member, which is a pointer to a next one of these things, and a function called data. Now, I rewrote the format of this. I'm not sure if it has the same meaning, or it should. As theirs is smaller. Find the one in the header file. Read data chain. Here's the create thing, and where's the other one? Data. Here, just a strap. Now there's some business about alignment, but I'm not going to worry about that. Now data says this plus 1. well, this is a pointer, so that means pointer value, and adding one does not add one byte to a thing because it's not assembler. So this expression should be address of this plus size of pointer to this. That's what I have, I think. Okay, I cast this as a pointer to bytes, and then add size of pointer to this. So that works out to be the same, but it's more typing, but I think it's clearer what this is, where this is. So it appears as though a C-plex or TS-plex is a kind of a linked list where the data part lies in between the next pointers. You see what I mean? There's data, and it's immediately following this, and all this is a pointer value, right? So it's like this picture I've drawn with a pointer, and it points you, well, it may point you to another one, or sometimes they get freed. So I'm not sure what happens in that case. Obviously this one's next. Yeah, this one's next would point to a different next, maybe null at the end. And it's up to you to know how long the data is. There's no indication in this class. The way it's used in the map thing is to store something of a fixed size, so there's no worries about that. Okay, so that's plex. Now, this is what they call an associative array. Now, I remember looking it up, in fact, the meaning of the word hash in computing, or hash table, and sorry, I just got back to this. I found that clip, but I guess I'll just clip in from an old tutorial, a little bit that I found out about hash keys, or hash values, hash tables, and all that, since it's explained best in here. Okay. This is great. So suppose you have a library full of books, okay? One thing you can do is you can just stuff all the books in the library, and be done with it. In fact, that's the way books were pretty much stored up until the 16th century, all throughout the Dark Ages. All these monks were writing these books, but they didn't sort them or anything. They just laid them down, And that one of the difficulties for historians is not so much that there isn't a lot of information available, but there's no way to find anything in it because it's all just randomly thrown about. Anyway, so you could do that. You could just throw everything in at random, but that's not going to be very good for someone who wants to come and asks for a title of a book, and the only way to find it then would be to start at one end and slowly go through each and every title until you find the one that you want, right? It would be better if you could sort them in some way to speedily retrieve the book. Okay, so here's one way that you could fill up the books in the library. One possible way. One way is, A, B, C, and so on. But here's another possible way. You devise a clever method. You take the title of a book and you run it through a little computer program, and the computer program spits out two numbers. One, a shelf number, and two, a slot on the shelf. And the librarian, when they are to store the book, they simply do exactly what the computer program said. It doesn't matter how that algorithm works. You simply do whatever it says. And the algorithm is designed such that it will always produce the same output as for the same input. Okay? Later on, if somebody comes along and wants to retrieve the book, they tell you the title of the book, run it through the algorithm, and where it had previously told the librarian to store the book would be where you would retrieve it from. So you go there and you get the book instantly. Now what you've done is you've taken a variable length title string and turned it into two numbers, fixed length thing, and used that as the way to store and retrieve books in the library, and provided there aren't any collisions, then you can instantly store and retrieve the books from the library. And that's essentially all there is to hash. You wouldn't believe how long this recording actually was initially, as it is now. I can't show you. I can take a print screen. I just took a print screen of the recorder's time, and hopefully at this point it'll only be like 2 minutes in, 2 or 3 minutes in for you. But here's what I'm currently at 50 minutes, slowly going back and forth over these things. And now that came up in the context of this project, the project I'm working on, because you remember I said that I'm loading up all these keys, and eventually this table is going to get quite large, and the program will take too long to load. So I'd prefer to load these things up manually, right? I mean, not manually, but on demand. So if I select a particular entry, it won't have been loaded, but I'll load it at that time. And I would like to store the ones that I've already loaded in some kind of an array. Now, it could be an array or a linked list or whatever. But now, if you look at this here thing, what we have is a great big structure on one side, and a numeric value, big number, on this side. And this, to me, is a perfect example of something that a map would be useful for. like this is an example where one of those associative arrays is exactly what you want. That is, like, you have an array, and you would like this to be the index number for the array, and this is the value, right? Now these numbers are, as you can guess, quite big. This one here, well, it's how many digits is that? Well, that little fit in calc. Oh yeah, it fits. Divide by 1,000. So that's 10 to the 3. And that's 10 to the 6. 10 to the 9. So I've divided by a billion, right? 10 to the 9, like gigas. And I've still got more to go. That's 12, 10 to the 12, 10 to the 18. That's what, this is 130 times 10 to the 15. Great big. That would be what you would call a big number, right? It's a huge number. It's the number of 100 nanosecond intervals that have occurred since the year 1600 AD. Well, of course, the last 4 are always 0, so those don't really count. They don't change at all very much. The first 2 aren't going to change very much. The changes seem to begin around the 5th digit. So, but still, it's quite a lot of digits. We got 3, 6, 9, 10, at least 10 digits worth of information in here. And you wouldn't want to declare an array with 2 to the 10 possible entries, right? I mean, it wouldn't, the program won't compile, right? Well, it might compile. Sorry, not 2 to the 10. 10 to the 10 possible entries, right? So what's in that in power of 2? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I want the log base 2 of that. Move log. That's 2 to the what? Well, here's log. How does this work? That's going to be log base 10. Yeah, that's log base 10. I want log base 2. Well, it's a lot anyway. 10 is 2 cubed about, so 2 to the 30, right? Ish, more than that, 2 to the 32. So okay, that's like 1 D word, or an array 4 gigs in length, where there are only a couple, a few dozen entries. Now, so the way an associative array works is you could use the associative array the way you would use an array that had 4 billion entries, but you don't make 4 billion entries. You just allocate them as you go along, and the way to do that efficiently is to use a hashing algorithm. We changed it. A file time, that's like a long, so it's got 2 D words, and you can turn that into a 64-bit number by just taking the high bit, casting that as a keyword so that you can raise it up 32, and boring that with the low bit. Which you could also, if you like, turn into a 64-bit number. So that's the time in coordinated universal, like the Greenwich time, the time in London. So to get, for instance, to get my time, I would have to add 7 hours to that. Okay, so now I want an array that uses this as an index, right? Or I could use it maybe a D word or whatever. I can use the standard map thing will allow me to use this as an index. But let me just show you what I mean. So I might say, suppose I've already built this thing, map, which uses this for the key value, and I want those that list. But I'll just put something else in instead for now. Whoops. This is the syntax. And then I would be allowed to say map the time equals, it wouldn't be a string, it'd be what were they called? A named buffer. Something like that. See? And so now this doesn't have to, that this is 64 bits, even worse than 32. That's not an array of, 2 to the 64 elements. It's obviously, it's just allocating as it goes along. And again, as I said, to do that efficiently, often a hash algorithm is used, what they call a hashing algorithm, to create something called an associative array. This is an associative, or could be an associative array. Now those words have meaning, but the meaning will become clear in a minute. First, I wanted to just mention that the idea of a hashing function, as explained in this video, is something that maps, generally speaking, a variable length thing into a fixed length thing. Okay, that's one type of hashing algorithm, is a thing that takes a variable length piece of data, like a string or a name or something, and turns it into a fixed length thing, and that allows you to create an association between those variable length things and something that's easy to store. And maybe that's where the word associative comes from. But the key to it, the key to a hashing algorithm working well is in that, given the data set that you're working with, like here's my data set, right? That the result of applying the hashing, which is something that removes information, like it'll take this long number and turn it into, let's say, a 2 or 3 digit number, right? And we want it to do that. You want the algorithm to do its data loss in an even-handed way. That is, what happens is you split this huge set of 2 to the 64 numbers into a very small set of what they call buckets, and when you add a new item to the map, it's going to go in one of those buckets, and you would like that the selection of bucket be equally probable for each of the buckets, optimally so, and that way you're going to get fewer collisions. Like, you're not going to get 2 things going in the same bucket as often. In fact, typically the buckets will contain more than one item, and there are collisions, and that's fine. That's expected. But what you want is to minimize that and have the information distributed as evenly as possible amongst the buckets. Well, that's related, as you can probably guess, to the idea of a random function. Like a randomizing function. Take, for instance, I have a function called random range. Okay, this is the one I thought I'd discuss, which takes 2 numbers of lower value, right? It says here a minimum possible value and a maximum possible value, and it is to return to me a number that is within that range, and with each number being equally probable. Okay. Now I wrote that function and I tested it, and I believe it is an even-handed function. That is, that the numbers do occur with approximately equal probability within any range I give it. But to do something like that does require more than just a little bit of thought. For instance, I made up an example of a bad one. Okay, here's one that would not be good. I'm going to show you that it's no good. It's not a very good random range function. Now, what this random range function does, given the 2 values, is it takes the random number that is provided by rand, and then takes the remainder of that when divided by the difference plus 1. So, and then add to that below. So, for instance, if I say let's say I go from 20 to 70. 72, okay. I'll just copy that. Character. Whoops. Okay, so now first, hopefully it won't return a value outside of that range. And it won't. You can prove that because this thing can only be between 0 and low minus high, right? The plus 1, for instance, an example would be, here's a range that includes 1,000 possible numbers, right? So high minus low would be 999, but there are 1,000 digits, so I gotta add 1. But the highest possible return from this is 999. Then if I add the low bit, the worst case, the lowest possible value is low, and the highest possible value is low plus 999, which is 999. So that's correct. And you can run it, you can test it yourself, and you'll see that's true. Now, running it once certainly doesn't show me whether or not it's a good random range function. But let's just see it run. Now, I'm assuming rand here, of course, is also an honest function in terms of what it's supposed to be able to do. Let me bring up the help on it. I did press F1, but this might take more than one, unless you want to sit here and listen to me for a couple hours. Returns a pseudo-random number between 0 and what's called randmax 32767, right? You have to call srand, but that's been done. Common already did that, and it doesn't matter anyway, at least for this test. Okay, the value I got back was 30. Now if I did it, let's say a couple times, more than once, I'm not going to get the same value. So we'll have an idea, of whether or not it's giving, it's doing something. But the question is how to show whether or not it's providing the numbers evenly. Okay, now it certainly looks fairly random. Now, one thing you can do to get a better picture, when I've got it down here, is make a loop. Not so many. Let's say 5,000. I chose a range from 0 to 999. I put the assertion here. And I don't have this yet. I'm going to do that. Put this down here. What I'd like to do eventually is count up the occurrences of each number. But let's just have a look at this printout and see if it looks like we're getting a fairly even range. I mean a fairly even distribution. And what you'll see is that from just looking, it's hard to tell. So it's really quite difficult to tell. It's 5,000 numbers. And as you can see, they're all over the place, and it's really, from this output, it's pretty difficult to tell whether or not that's an even output, right? Whether each number is equally likely. Alright. No need to give up. What we can do is do what I have here. What we'll do is we declare an array, 1,000 big, zero it out. Right? That declaration will zero this out, even though sometimes it won't zero everything out, but for an array it will. And we'll add this line here. And we don't really need to do this part. What we're interested in now is are the values in this array, because this array is going to count up, give us a number of times each of the numbers between 0 and 999 got picked. So what we can do at this point is run through this array, which is 1,000 long, and now what we can do is print them all out, or just say, let's say, if I'll print out the non-zero one. Call it index. Nope. We can do them all on different lines. Try it like that first. So for the the ones that did get hit, we'll get a count. Now that could be as many as 5. Maybe I can do 2 per line. Well, we'll see. We'll see. This will give us a better idea of whether or not the numbers are being evenly distributed. Like if we see that some of them are very high numbers. Okay, so you can see, oops, not 5,000. This could have been called index 2. Here, actually, this one doesn't need this value is unnecessary. Right? And in fact, I can do it all in one step. Make it nice and clean. Okay, now they're all little numbers, right? It's kind of difficult to tell whether they're coming out evenly or not. It looks pretty random to me. So far, I don't see any evidence of a weighting towards higher or lower numbers or what, right? And nor should I, because it's not a very good way of doing it. A better method, really, I would say, is instead of doing keep this array, but we can go by groups of 10, let's say, and print out, or groups of 100 and print out 10 answers. I've got that. In fact, I've got it general down here. Oops, missing something. I did this before and I tested it, so this code should work. Let's see. Invent another array. Well, first let's try 10. No, it's going to have to go. It's going to have to work out evenly. I want the same number of elements from here in each group, so we can compare them. So this has to be this group. Sorry, this thing. The number of elements in here has to be an even multiple of the number of elements in here. The lower groups seem to get less. Suppose I switch. Suppose I add even more. Let's see if that theory still holds. What we're doing is we're analyzing the distribution of numbers in this for this generator, and the generator is clearly weighted higher. It looks higher in the middle. When I change this to a 5, you're really going to see. Oh no, 20. Okay. Now, this is happening over and over again, and this difference is significant. That's nearly 3,000 different, and it's in the last of those 5. The other ones look even, and with pretty clear consistency, that last one is much lower. If my range, I take a simpler or a smaller number as an example. Suppose it's that the random function gives an evenly random number between 0 and 2. And we want to generate a random number. Or no, let's say suppose it's 0 to 10. And we want a random number from 0 to 4. And rand max is 9. So we don't have an even number of groups of 4 in our range, right? There's these 2 extra ones. And so some numbers are going to be more likely to come out than others if we're taking the remainder, right? 0 gives remainder 0. 1 gives 1, 1. 2, 2, 3, 3. And then now at 4, go back to 0, 0, 5, 6, 7. 0 and 1 occur 3 times, whereas the other numbers only occur 2 times. And that's because the range doesn't divide evenly into the subrange that we want. A long time explaining a very simple concept. The point is that the question of generating a hashing algorithm is intimately tied with the same question of finding something that gives an even output, right? No clumping. This thing that gives clumping, so it's no good for a random distribution. And in a similar vein, to make an associative array depends on a good one depends on 2 things. One, the range of input, the type of data that's being input, and the buckets. The input value should result through what they call the hash algorithm. The hash number returned should give an equally likely chance to place the item in any one of the buckets. Now, of course, that's impossible to do. But it turns out that you can get stuff that's pretty close. So what I did then was I wanted to see one of these things in action. And I guess I'll get to that next tutorial. I looked at the CMap class, which uses a hashing algorithm. And I took their class and I made my own version of it here. And I guess I'll get to that next time. This is going on for quite a bit, a lot longer than I expected. It's a simple little class, and it does seem to work, strangely enough. Well, go over it next time. Hopefully, you'll enjoy walking through it with me. We'll do it together. Okay, see you.